Introduce me.
All right. Good evening, everyone. So welcome to our Caltech Astronomy Lecture and Stargazing event. So for the information of our newcomers, we're running this series of events every month. And our next one will be on November 1st by Professor Jim Fuller on astroseismology. We also run a series event called Astronomy on Tap in a bar in Old Town Pasadena called Dare Wolf. And the next one will be 2 weeks from now on Monday. So if you prefer to listen to astronomy while drinking, that's a good place to go. So we're going to start this with a half an hour lecture. After it, we're going to set up the Q&A session right here, as well as some telescope outside on the field. The Q&A session and the stargazing are going to happen simultaneously. So feel free to walk in and out in this room and just ask us questions and also do a stargazing outside. This whole event ends at 9 p.m. For stargazing, our targets tonight are the Moon, the Jupiter, the Saturn, and maybe Albireo. I'm not 100% sure on that. The Albireo is basically just a binary star system with two different stars, two very different colors. Before I introduce our speaker tonight, the last thing I would like to do is to acknowledge our volunteers tonight. Nikita, Rainier over there, and Michael, I don't see. Michael is running the overflow room in the library. Also, Lee is going to be our panelist on the Q&A session. Our telescope volunteers are Andreas on the field, and also 5 PCC students. They are Stephen, Brooke, Joseph, Matt, and Eric. I'm Yu Guang, and I'm hosting tonight's event and also taking pictures. Our tonight's speaker is Dr. Alessandro Schillaci. I hope I pronounced that perfectly. He was born in Rome, and he got his PhD, not surprisingly, from the University of Rome. After that, he went to various places, including Princeton and Chile. And finally, in 2016, he came to Caltech working on BICEP, which is an experiment in the Antarctica to test the theory of inflation after the Big Bang. And I'm sure you're going to hear something about it tonight. That being said, he has been to the South Pole 5 times already, and is about to start his 6th in next month. Is that correct? Yeah. So if you have any questions to him today, don't miss the opportunity to ask it, because after a month, you suddenly realize, oh, I forgot to ask something. You're going to go to the South Pole to find him. Aside from his professional career, Alessandro is a very passionate astrophotographer. He always sends me emails to show off the amazing pictures he took through the weekend. And I'm sure you're going to see some of his work as well. So today he's going to talk about an ancient paradox, why the night is dark. The night sky is dark. So without further ado, Alessandro, please.
Thank you. Thank you. Okay. Can you hear me? Can you hear me clearly? Okay. So thank you for coming. He already said a lot about me. So by the way, so let's go into this question. It looks like obvious question with an obvious solution, but actually is deeply connected to how our universe is. Okay, and obviously obviously the solution of the question is not this. Okay. So let's go deep into this question. So this paradox is known as Olbers Paradox, but it's actually, the question started longer before, in Greece with philosophers, and he went through the time, and he came to this with this name because this was one of the astronomers that actually put it on paper. Okay, but another famous person that did it was Edgar Allan Poe, okay, that spoke about this paradox. The paradox is basically the consideration that if our universe is static and infinite and infinitely old, basically wherever you are looking, you will meet the light of a star. and basically the sky cannot be dark. It will be bright, okay, wherever you're looking. To solve this paradox, we need to take a very deep look into the universe. Let's start it. So we are here. So actually, it's night at this point. We go farther. This is Los Angeles. We are there, okay, on the west coast of the United States. And we are not here, unfortunately, because we could enjoy a beautiful ice cream. But anyway, let's go farther. So we are here. You can see that we are leaving actually our solar system. That's the sun. We pass by Saturn. How you could leave the solar system without watching Saturn the last time, right? And we are there. This is a beautiful picture of Cassini that you may know. So, and we are there in that small dot. It's pointed there. We are there. So this is obviously computer graphic because we never traveled so far. This is the view from Alpha Centauri, okay? And that star is our sun, because at just 4 light years, our sun looks like a star, okay? A normal star, not so bright, okay? We go farther, and this is our neighbor, the star that actually are around the sun. We are there. This is our galaxy, the Milky Way. It's actually, our galaxy is a little bit different, we know. It's, yeah, oh, sorry. I may use that, maybe. Actually, I prefer. You make me something. Okay, better? No? Now better, okay. Much better, I can see, I can listen, okay. So we are in a galaxy, a spiral galaxy. It's actually, I was saying, it's not that shape. It's a little bit different. We know it's barred. It has a structure in the bulge. Okay. This is our local galactic group. We are on this faint spot that is made by at least 100 billions of stars. And we have another big galaxy closer. Not that close, actually, 2.5 million light years, that is called Andromeda. And these are tiny galaxies that orbits around these two big galaxies, okay? We go further, and we are here. So this is our superclusters, okay? Because with our local group of galaxies, we are part of a bigger concentration of galaxies, thousands of galaxies, that is called Virgo. And then we go further, and we have many superclusters, okay? And then we go further, sorry, and that is basically the large-scale structure of our universe with supercluster dispersed in this huge space. What happened after? So what happened? What we could find after the farthest galaxy that we discover? So here you can see basically a slice of what the astronomers map in the universe. Each dot is a galaxy, and this is the farthest discovered until now, I believe. I don't study galaxies, so I don't know if there is another one farther now, but it's a remarkable 13.4 billions of light years. So what we observe is basically this light that traveled for that time, okay? So basically is a galaxy that the light travel, we will see for most of the age of the universe, okay? What we can find after, what we can find if we look deeper with I don't know, a bigger telescope or something, new technology or something else. Well, to understand what we can find, okay, we need to go back, actually here, close to Los Angeles, on these mountains that you can see on north. Basically, on one of the mountains you will see some antennas, okay? And on the back of those antennas there is a dome that is pretty famous. It's Mount Wilson Observatory. Where this astronomer, that is the famous Hubble, Edwin Hubble, working for the first time with this telescope that was brand new at the beginning of the century, he finally gave us a clue for understanding what we can find after the last galaxy. At the point, actually, there was a big question, because the astronomers, they were looking these faint nebulas, spiral nebulas, because they didn't know about galaxies. And the question was what they are, how far they are. And Hubble, with this telescope for the first time, was able to find the answer to this question. That was a big debate in the astronomy community. How he did? So basically, he looked into the closer galaxies, and he found out, this is an original picture, and you can see that he marked one star. Okay, so he found out that some of the, first of all, the faint lights, these spiral nebulas, they were made by stars. Okay, and some of the stars, they actually were varying their light, and they were varying the light in a very typical way, in a very precise way. So basically, he found out that those stars, they were actually the same as some star that we have in our galaxy called Cepheids. Okay, and these stars, so they vary their luminosity. Okay, with in a relation, in a time relation with the luminosity that they have, and they can basically be used as standard candles for measuring the distance. Okay, this is the star, a picture of that star taken in the recent time. Okay, what came later with this discovery? So that was already a huge discovery, because they demonstrate finally that the galaxies were made by stars. They were basically other systems, okay, in respect to our galaxy. And they were further, because measuring the distance of the stars, they found out that the galaxies were at millions of light years, not just thousands of light years like the stars, okay? They were outside our galaxy. Another thing that he discovered, measuring the distance finally of these galaxies, he discovered that looking to the light of this galaxy, so the light of this galaxy was basically looking redder and redder as much this galaxy were actually farther than us. Okay, so basically he found out a relationship between the distance of the galaxy, okay, and the velocity in which they were recessing from us. How? Because you ever experienced, for example, with an ambulance, the sound when this ambulance is coming closer to you, the sound looks with a higher frequency, and then when it passes by, it looks actually with a lower frequency. Okay, it changed the pitch basically. That happened with light too, because light is made by waves, okay? And what happened to the light is that as much the galaxy is moving faster in respect to us, as much the light moves to red, okay? This is called redshift. Basically, Hubble, and that was a very huge discovery, found out a relationship that allow us, just measuring how fast the galaxies are moving away from us to the distance. And that is the Hubble law. Okay? Perfect. So with that tool, finally we had a tool, with that discovery, we finally had a tool for measuring the universe, the galaxy, the distribution of the galaxy. And And a consequence of that discovery, measuring these speeds, this galaxy, a consequence of that discovery was that he demonstrated that our universe wasn't static; it was expanding. Okay, and the light of the galaxy was reflecting actually that expansions. Okay, so by the way, from that moment, we're speaking about 1940. So we we finally had a change of the model of the universe that from being static was starting to be considered actually a expanding universe. And actually not working. So there was a video here, but it wasn't working. Oh yeah, okay. Okay, so basically what you have to consider our universe, if you consider the galaxies on the surface of this balloon that is inflating, so you can see that each galaxy actually see the other galaxies moving away from itself, okay? And that is what we are experiencing, because if Hubble from our point of view, he was watching all the galaxies and he saw that all of them, they were actually moving away, okay? The other things that show this graph is that if you look at this wave that is supposed to represent the light, now it's not moving anymore, okay, maybe? No. I'm sorry. Maybe I need to go back. Okay, now it's moving again. So you can see the wave that when the balloon expands, that represents the light that is propagating in the universe. You can see that the wave became wider and wider. Okay. And it changed frequency, and that is the reason why we see this shift of the light from on the red, in the direction of the red. So, by the way, from that point, we finally have this universe that we finally demonstrate that the universe was expanding, and looking back in time at the point, you can think to the beginning of this universe. So because if it's expanding, it means that all the objects at some point they were actually concentrated in the same point, and from the moment that we finally start to speak about a Big Bang, so an initial moment of the universe where all the energy, all the things that we are looking in the universe, they were actually in the same point, concentrated in the same spot of the universe, in the same volume, in the same point. So by the way, so this partially was solving the paradox that we were speaking at the beginning, the Olbers Paradox. Why? Because one of the conditions of the paradox, that the universe is actually infinitely old, is actually missing at this point, because the universe is not infinitely old, because it starts at some point in the past, okay? Because we have a Big Bang. Is this fixing the paradox? Actually, no, because immediately after that, the physicists, they were starting to look into this universe back in time, became smaller and smaller, okay? And becoming hotter and hotter, okay? And that means that when we look back in past, this universe should look brighter, okay? Because it has to become a hot and infinitely densely place, okay? Basically brighter as the sun, because at some point all the matter has to be so concentrated, okay, that you should look into basically a bright light coming from the universe, okay? Because when we look far, we look back in time, okay? And if we look deep into the universe, we should see this universe becoming so bright. What is the solution? The solution is again, the solution is again that we have to look at the universe in terms of space-time. So basically when we look far, we look back in time, and the universe is expanding in this time, okay? So by the way, when we look back and we look, this universe became simpler and simpler, hotter and hotter, we have to consider that that light that we are looking coming from the past is actually expanding, okay, in the time that is traveling to us. And by the way, it became fainter because the frequency moved to fainter, to microwave, radio waves, and it became fainter. So by the way, so the paradox is still not fixed if you look at this. Let's go ahead and see what we discover. So, in 1964, these two scientists, these two physicists, they were working on this microwave antenna, and they detect a weird signal, okay, that at the beginning they were thinking about pigeons inside the antenna, okay, and they start to look, so you know, when the scientists find an issue in the instrument, they start to look into to unmount it, remounting, cleaning, you know, doing whatever. So also sometimes you know, things that kind of, so because they did that time in that way, they fix the problem, okay? So something like there is an historical, you know, believing, okay? They didn't get rid of the noise, and at the end they found out that actually the noise, it wasn't a noise, but was a signal coming from sky, okay? Coming from everywhere. So basically, what they were looking was this light, okay, in microwave, the still light, okay, coming from any direction they were pointing this antenna, okay? See, the antenna has a bearing, you can actually move it, and this is the telescope, it's a mirror, okay? It's an off-axis mirror. Basically, the radiation comes from here, get reflected, and go into the cabin for being detected, okay? So here, you can see something that come just later, okay, in 1980, I think probably 82, if I remember correctly. COBE, no, it's 1992, sorry. With COBE, that was a NASA, sorry, was a NASA satellite. And it was sent to measure the signal with extreme precision, okay? And it did this map of the sky that you can see is probably the most boring map ever made of the sky, because you can see it's just a map that shows that the sky is bright, okay, with this brightness that we use temperature to indicate this at this frequency, the brightness, okay. What is it? The light. So actually, the light, okay, is the background of our universe, okay? Is the light that we were supposing to be there because we know that the universe, going back in time, became an hot place, okay? An hotter place. So that is basically the afterglow of our universe, of our Big Bang, of the beginning. So after COBE in 1992, that basically we pass from this kind of map. You can see just you know, this tiny signal of our galaxy, okay, as a feature. We had COBE that start to see a little bit clearer. Then we have WMAP, that was an awesome mission, and finally we had a clear detection of what we call anisotropies, okay, in that sky, in that microwave sky. And then we have Planck, a mission of Europe, in which we have the most detailed map of this microwave sky. And this is the map. So basically, you have to think to this map as a map in which you have removed the average signal, okay? And you see only the tiny difference, okay, of brightness, okay? How tiny? So we are speaking basically 1 part over 10,000, okay? So basically, if the temperature or brightness, I told you we used temperature, it was basically equivalent to 2.7 Kelvin, okay? That means very, very cold, okay? It's a universe that is cold, because this radiation got diluted into all the history of the universe for the expansion, okay? So the anisotropies appear to be basically at the level of 100 of micro Kelvin, okay? A very tiny difference of temperature. What they are, these spots that we can detect in this microwave sky? Well, sorry. If you start to count how many spots of certain size you have, you find that they are not randomly shaped or sized, okay? They have a precise physics inside, okay? And you find that most of the light, most of the spots, actually they have 1 degree psi in sky, okay? And that's actually is very important because it gave us an idea about the condition of the universe at the epoch, okay? So what we are observing with the map is basically the plasma, the hot universe that we were talking about, okay, right after the Big Bang. We're speaking about just 380,000 years after the Big Bang. And that is the plasma bubbling, okay, in which, you know, sounds, waves are propagating, okay, and they can thermalize the plasma only at that size, okay? So basically what you're saying is that so the spots are of that precise size because one spot here cannot have the possibility to communicate with another spot just on side because the temperature couldn't have the time to propagate in the just 380,000 years after the Big Bang. That is the age of when this moment happened, okay? To study this map, we use basically this graph, okay? And when you got measured the first time, we have one experiment that was made from Caltech in Italy, okay? Rome in particular, where I was studying, called Boomerang. That was the first actually to see clearly this peak, okay? For the first time, it was a balloon launched in Antarctica, okay? And the first, there is a famous paper in Nature in which you can see this graph, and where I took them. Basically, this information about how big are the sound waves at that epoch, so close to the Big Bang, gave us basically a tool to measure how is the geometry of the universe from us to there. It gave us basically an idea how the universe is curved or not by the matter, the energy that is inside the universe. Why? Because if you think to look at the map with your eyes, okay, you will see a different situation if the universe is curved by the presence of matter, because we know from Einstein that the matter curve, deform, perturb the space-time. And since we see exactly what the theory predict, okay, we see this peak at 1 degree, okay, so basically we demonstrate that the universe is basically almost flat, okay. This was acquired in 2003 by this experiment, Boomerang, for the first time. So let's go ahead. What else we can? What else we can say? So one first consideration when we look at this map with this spot, that is the whole sky. So wherever you look, you will meet that surface. We call that the last scattering surface. What we can say? Well, so we can say that we are observing from here, and since we are observing from here, it looks like we are in the center of this universe from what we observe, but just apparent, because what you observe is actually we have to consider the time when we look into the universe. And what we look basically is back in time. By the way, when we look far, we look back in time, and we look a universe that is actually confined into this surface of light, okay? So actually this finally solved the paradox, because you just saw that the universe is actually, the sky is actually not dark. It's dark for our eyes, we cannot see it, but if you can look with microwave telescope, you can see actually that it's not dark, but it's bright. So Another consequence is that actually this surface is something that is kind of limit. We cannot look further because it's a bright surface, okay? We cannot penetrate it. It's plasma. Imagine to look into the sun. You can't, okay? Why? Because it's plasma. It's made by charged particles. These particles interact with light and they stop light. They absorb light, okay? They scatter light. And we cannot get further, okay? So basically we are confined. Our vision of the universe is confined into a sphere that is centered on us just because we are looking from this point. If you imagine to look from Andromeda Galaxy, the sphere will be centered on the Andromeda Galaxy, okay? Because it's the distance that make that sphere appear, because the distance means time, okay? So basically looking far in the universe is looking back in the time. A telescope is a time machine, especially in microwave, I can tell, okay? Okay, how we could possibly look further? So what's next, okay? Here I forgot to put, but these are pictures that I shoot. This is Antarctic, this is Chile, okay? They look similar, right? Just different colors, because they're both desert. Okay, what's next? Okay, so we arrive here. This is all the universe we observe. That is a large part, okay? This is a graph that, looks like that we don't know a lot, but if you see the time scale on the bottom, you can see that actually this is a large span of time, okay? We're speaking about 13.8 billion years. But the first 380,000 years, we cannot access them because our vision is stopped here at the last scattering surface. What's next? Well, the theorists, looking at this surface and looking at the graph with the peaks, they made models, okay? And the models, they predict actually that we can go farther observing that surface. Because, why? Because, see the Big Bang, we believe, because the models, they fit with that prediction, that at the beginning, just in the first instant moment of the universe, there was this exponential expansion called inflection, okay? The inflection looks like something like why. So why you guys came out with this idea? The inflection actually fix a lot of problem of the universe that we doesn't have the inflection. Because if we don't have the inflection, basically what happened is that we need a very precise initial condition to get the universe that we have with a flat geometry, okay? If you don't have inflection, basically we are saying that we found out that the universe or doesn't last more than a tiny second, okay? Or it will expand so fast to don't form anything, galaxies, stars, whatever, okay? What is the prediction of the inflection? Well, if we have the inflection, what we should observe are these perturbations in the plasma, okay? That they move, especially density waves, okay? And gravitational waves, okay? And these waves, they propagate into the plasma for the initial 380,000 years, and they should have left an imprint, a footprint, a characteristic footprint in the last scattering surface, in the CMB radiation, in that map we are observing now, and that we cannot penetrate, okay, with anything. We don't have an instrument to do that. So by the way, we can go further, and here you can see that actually these signals are very special, very particular. They are polarized. What means polarized? Means that the light that is away propagates with a special plane, a preferential plane, okay? And if you look, so this is the same, different math on side anyway, but this is the very same graph we saw before with the peaks. We saw the theory predict that this polarized signal should have a very specific pattern in the sky, okay? Especially for the density waves, you should have what the so-called E-mode pattern, that is this kind of pattern of, so you know, it's a polarization pattern. Basically, it means the vector means the direction in which the plane of the waves is oriented, okay, or the propagation waves is oriented. The gravitational waves that are deeply connected with inflection, they should have left an imprint in the form of B modes that are kind of spiraling, okay? How we could detect this signal? Well, if you look at this graph, you consider the number on this side, you can see that actually if this is the temperature and it requires, so let's say 30 years to get the instrument for detecting the anisotropy on that. So we are speaking to going down, see, 1, 2, 3, 4 order of magnitude, okay? So basically we need a very sensitive instrument. This is the next challenge of cosmology, okay? What we are trying to do here. So basically we want to detect a signal that they will give us an idea about the energy scale of the inflection of the Big Bang, so basically, okay? But this signal is super faint. Okay, if we're speaking about 100 of microkelvin, now we are speaking about nanokelvin, okay, under the single microkelvin, okay? How we can go so deep? So, well, it's not just faint, it's also confused in the signal of our galaxy, okay? This is the galaxy in the microwaves. You can see that all the dust emits radiation, okay? In the very same band, the microwave, okay, is overimposed on our signal. And also, the radiation that comes from the last scattering surface, from the CMB, it travels all along the universe through the cluster of galaxies, that structure that we saw, and they get perturbed, okay? So by the way, that is another effect that we have to consider. We have to clean basically our signal from all these effects. Now you can start to understand how challenging it is, okay? Oh my God. So, well, so that is the reason why we face the deserts for trying to measure it. Why the desert? Because if you look, this is a simulated atmospheric transmission spectra. And these are frequency in the range of microwaves, okay? Speaking about hundreds of gigahertz, sorry. You can see that actually the atmosphere is pretty transparent in some bands, okay? That is if you go in a desert, that is because the water vapor is a very big emitter in this band. Okay, the water vapor, the water basically in the air, and that's this is a map of the world that show how much water vapor is in the air. And you can see that there are some areas that are actually very good, and you can see that, for example, Antarctica is one of the best. Okay, Greenland, Tibet, Atacama, the desert. So that is the reason why we go to these remote places. Oh my God. Okay. This is one of the first places, okay? Atacama, the desert of Atacama. This is a telescope, I'm showing it because I work for this telescope, okay? It's close to Alma, okay? Actually higher than Alma. In fact, I was working there for a year, okay? Every day coming from this town down here at 2,500 meters up to 5,200 meters. First days with oxygen, otherwise you will not tell it. You will not tell the story to nobody, okay? And this is the telescope, 6 meters, okay? Watching the sky. You can see the environment, okay? It's a desert, believe me, it's a desert. We are speaking about the desert here, but not desert as that. First things, you also have this impact with dust that we close your breath, okay? The first days. Then you get used, but it's not good. So I can show you, oh, no. Sorry. Okay, it doesn't start. I don't know why, but I can do it. I can show you a video that I took when the desert, just in one day, became like this. Okay, because just a few clouds entered the desert, and they just so the clouds just fell on the mountain. Okay, and they left their snow. Yeah. And this is under the snow there is a road, okay? Believe me, there is a road. And we managed to reach the site with the chains, okay? To operate the telescope. Okay, this is the other place, the place where we are going on November. And we have a long history of instrument in this place. It's South Pole Base. And these are Keck Array and BICEP 3 that is here, our telescope. There is another telescope that is a huge 10-meter telescope, also in microwave, okay? That is the same kind of telescope of ACT, the one in Atacama. And, there's another video here that show one day there. So this is the path that we have to do every day for going from the base that is there to the observatory that is just on my shoulder, on my back, yeah. And it's a kind of kilometer walking, okay, crossing the landing line, because we are in a sector that is called the dark sector, because we don't like, obviously, any radio signal or machine moving around, because they can give us a signal in our instrument. They are so sensitive. Remember, we are going to measure nanokelvins, okay? And this is a video that showed that walk every morning or every afternoon, because we are coming back for lunch, probably for dinner. Obviously, it's a career that proves you a lot. This actually is the Italian-French base, Concordia, that is even worse than South Pole, taller, 500 meters taller. Okay, it's on a dome on the East Antarctica. And this inside the cabin of Earth in Chile, where after a day of greasing the telescope, because the grease sprayer, they decide to don't work for a month, and every day we have to grease by hand the gears. Otherwise, 100 tons of telescope we will not work anymore after a day. Okay, and they happening at 5,200 meters, as I say. And obviously, in mind you have only science. But even not. Okay. Okay. So let's see what we will do on November. We travel from United States to Australia and then New Zealand. Okay. And then from New Zealand there is a nice flight. Go to McMurdo on the coast and then to South Pole. Okay. So these are some of the pictures, probably some of the nicer I can get. This is not nice, but it's just to show that there is this place, okay, that is actually moving every year of 10 meters, okay? And there is a ceremony every year for repositioning, because the ice is sliding to the sea, okay? It's a glacier. Antarctica, it's a thick layer of ice flowing to the ocean, basically, in any moment. And this is the ice flight with the C-17, because the flights from the United States are managed by military, okay? Because it's very hard and dangerous environment. Oh. Okay. But with Italy, I went there 4 times with Italy. Italy, in French, they use actually a boat sometime, and they did a boat 3 times. And this is the sea between New Zealand and Antarctica. And you live in this for 7 days without end, okay? And without eating, obviously, because imagine. And if you want later outside in the foyer, I can tell you other stories about the travel in the ship. Now we don't have time. I have to probably go faster. So what do we do there? So we have this telescope. They relentlessly scan the sky, the very same spot that is a clean spot, okay? Because have you seen the situation in the galaxies? A huge signal contaminating the sky in microwave, but there are few spots that are actually less contaminated. Okay, there is no place in sky that is not contaminated by the galaxy. There is always a little bit, but there are places that are better, and we look there continuously, trying to accumulate data and data to go deeper and deeper. Because in this frequency, the biggest variable is how long do you observe the sky, okay? And these are few of the telescope. This is BICEP 3 Keck array that we put on field. Currently we have the red one, Keck array and BICEP 3, and the next one will be BICEP array, the one we are deploying now. See? Okay, so where we are. So I show you the spectra. We are speaking about going deeper and deeper to measure the spectra of B modes for the gravitational waves. We are very deep, but we still don't have a detection, okay? We need more data, we need more instrument. In particular, we need instrument to many frequencies, because here I show you the sensitivities. You can see that we have the galaxy with dust, a synchrotron. The magnetic field of the galaxy actually emit another signal, not exactly the magnetic field, but the particle that's spiraling around the magnetic field. And we need more data at different frequency for basically characterizing these signals. So this is the new telescope that we are building. This is BICEP array 1 that is here at Caltech, currently cold, and we're taking data. She's taking data, Chang. And this is the BICEP array 2, because the telescope will comprise 4 telescopes in a single mount. That is a huge piece of engineering, okay? And here is me with the guys in Minnesota, okay? That is one of the institutions that is working on this project, integrating the second receiver for doing tests on the mount, okay? Because in this kind of astrophysics or experimental astrophysics, everything can make the difference. See, even a small detail, okay? Even a small detail can give us a noise or worse or better measurements, okay? We need to take care about any details. Okay. This is the plan. Basically, we will deploy the first receiver starting on November 2019, 1 month from now. Here, in place of Keck, basically we are going to remove the old telescope, put a new one, a new mount. Imagine all the work we are going to do, and 1 new telescope plus 3 old ones, because we will take the tubes from Keck to put them back in the big mount together with the new telescope we are mounting. Because as I say, we need data. We need as much data we can collect. Okay. This is the collaboration. A lot of young guys. Here there are some. Chang, Silvia, Paolo. Many are obviously working, and these are the main institutions, but we are a lot of other institutions also contributing. And thank you for your attention.
All right. Thanks, Alex. Before we wrap this up, did I say at the beginning that this whole thing ends at 9 p.m.? Because that's definitely a mistake. It ends at 10 p.m., so you have 1 more hours to hang around, ask the questions, and also check out the telescopes. So any questions for the speakers? We can take a few.
Just a reminder that if you're going out onto the athletic field for stargazing, please no high heels, no food and drink. Thank you.
Please.
Thank you very much. I really enjoyed your presentation. It was fantastic. If you could talk for a minute about dark matter and the difficulties of dark matter, and if there's newer tech to observe dark matter and how that's going?
Yeah, of course, there is interest for that topic, for dark matter. In particular, our telescope is targeted to B modes, okay, to detect this signal. But for example, the telescope I work in Atacama, ACT, and also South Pole telescope, that is the other big guy that I show in the picture in Antarctica. They are trying to do those kind of measurements, okay. So there are two kinds of telescopes in this field, in cosmology. One is trying to get information about tiny structures, okay? Basically, the effect of those tiny structures in the on the microwave background, okay? And those are the big telescopes because they need resolution. They need a big dish to get finer resolution, okay? But the telescope that actually I'm more interested in are these large field telescope because I feel that that is actually a very big challenge, and so the idea of this surface that cannot be penetrated with normal light, okay, so we just having so you can have you can say, oh, I will use a telescope, a bigger telescope for doing that, and but you cannot, because I told you so, the light cannot penetrate. This idea actually to me is very intriguing, and I really feel that there is a challenging a field that I want to pursue. Yeah. Sorry, I'll give you back. Other question? Which one? Whatever, go. You want to know the temperature variation between the two? I told you, so we're speaking about the temperature map. The variation is on the order of plus and minus 200 micro Kelvin, okay? If you're speaking about the polarization map, the E mode map, so the signal that is induced by the density perturbation, okay? The density waves in the plasma, okay? This is the order of 20, 30 millikelvin. If you're speaking about the B mode signal, the one we want to detect, we are going 1 microkelvin or less. We don't know actually, because the theory can match different profiles with, more or less powerful inflation. Please.
Hi, good evening. So, concerning the images of the cosmic background radiation, the same topic, we saw 3 different images with different resolution. Is that correct? Right?
Which ones? The three square. Yes, yes.
And they are all fluctuation around the average. Is that correct?
Yeah.
Yeah. Why in the low resolution ones we saw a red line, horizontal red line?
Oh, I didn't see that. It was probably a big fissure. Let me see.
No, it's like really remarkably red line.
There was a big fissure.
High temperature net horizontal line, but
I don't know if it was a graphic mistake, but you can have actually, if the space-time is so bent, you can have actually very large structure, okay? Because the image is basically expanded by the bending of the space-time, okay?
But the red spots means high temperature.
Yes.
Right? So from the graphics, looks that the low resolution predicts a higher temperature on the let
me check. I wanna watch it. I don't remember now. Sorry.
Yeah, but why the high resolution one doesn't?
You're speaking about this. Oh, you mean this? Oh, you mean this? You mean
yeah,
this?
exactly. Yeah.
Ah, sorry. So that is the galaxy.
But why the high resolution? We removed. So there
Because what they do, the data analysis. So what they do is that they do a template of that, and they remove it, and they.
So in this one, there is no hold.
In that one, there was, but they replace it with a simulated, sky. So basically, there is a piece in the middle. That is kind of better realization of what could be behind the galaxy, okay? Because the galaxy here is saturating, okay? It's a signal at the order, I think, of milli-K, okay? It's actually 10 times or 20 times brighter than the anisotropies, okay? You have to remove it because otherwise it will false all the dynamic of the image, okay? When you remove it, you can have or a hole, just a mask, okay? Or you can fulfill it with a realization that is just a statistical way to fill that hole that is left by removing that, okay? Yeah, it's the galaxy, yeah. It's actually, they were seeing also with the whole telescope, see? There is a tiny bright line in the middle, okay? Because it's so bright, the galaxy, yeah. The one because it's becoming thinner is the resolution, as you pointed out. Yeah.
All right. I'll have to shut this down because we need to invite the Q&A panelist now. And if you have any questions to Alessandro, feel free to.
We'll be outside.
Yeah, he said he will be in the lobby, so you can ask questions in the lobby. And let's bring up the panelist.
And I want to say thank you to.
Thanks, Alessandro.
Thank you to them.
Panelists are ready, and they have their names up there and their specialties. So I'll just let you guys introduce yourself, and I will hand over the questions to whoever is interested in asking.
Hi, I'm Nikita. I'm a fourth-year graduate student at Caltech, and I work in X-ray astronomy, and I study supermassive black holes.
Hi, I'm Lee. I'm also a fourth-year grad student. I study exoplanets, which is short for extrasolar planets, meaning planets orbiting stars besides our own. I used to do things about dying stars, but now I just do planet stuff.
Hello, I'm Reinier. I'm a postdoc at JPL and here at Caltech. I'm also studying active galactic nuclei, but mainly from a radio perspective. So that's the other end of the spectrum. And I also specialize in development of instrumentation. Maybe our chair can also introduce himself and his specialties.
Galaxy evolution and also the circumgalactic medium, which is basically the gas around galaxies.
Thanks. Sorry, I think this isn't going to hit any of your specialties on the head, but I'm curious about some of the recent headlines about whether the farthest planet in our solar system may in fact be a black hole. I haven't read any of the articles. I've just seen these headlines over the past few days, and I thought it'd be something to ask here.
So this is actually this is a good question. I haven't read the paper in question, but sometime in the past couple of weeks. So the question was, do any of us have any thoughts about recent headlines about the fact that the farthest solar planet in our solar system, a planet which actually hasn't yet been found, it's known as Planet 9, and people think it's there, but we haven't actually seen it, is a black hole. So I skimmed this paper in the last week, and I think the idea is that if you haven't found something, if it's a black hole, that would explain why you haven't found it in an optical astronomy search, because black holes don't emit any light. I think the paper was more of a thought experiment than anything else, but I mean, it's good to explore all possible avenues of why you don't see something that you think is there, right? So I mean, Planet 9 is something that Mike Brown and Constantine Batikin, who are both across the street and professors in the GPS department, they sort of work on the search for this object. Constantine sort of did a lot of the simulations and theories that show that like the presence of another planet that's far away might explain some things about our solar system, might explain why Jupiter is in a certain place. But the search is ongoing. The one fun thing about that paper that I do remember is it has a figure that is 1 Earth mass black hole to scale, and it's a large solid black circle that fits inside an 8.5 by 511 piece of paper, and it's what the size of this black hole would actually be. But I don't think it's the most likely. I don't think it was posited as the most likely explanation. That's a good question, though.
So this might also be for Lee, since you used to study novae, but anybody can chime in. So we read from time to time about the possibility that there might be a gamma ray burst or a supernova somewhere in the relatively nearby stellar neighborhood that would, irradiate the Earth and probably kill everything here. And I was wondering, we've surveyed basically all the nearby stars. Has anybody said, well, all right, we've ruled out the possibility that something that energetic could happen, or we think that the odds are X?
That sounds scary. No, I don't think that's. That I wouldn't worry about it.
I don't lose sleep over it, but.
No, I mean there are no. Are there nearby?
If I remember correctly from quite a while ago, there are a number of stars indeed, which are fairly close, which could go supernova and irradiate us with a significant amount of hard radiation. I think even some of them are overdue, as in we had expected to get them to go supernova already, but it's a bit in the same category as the Yellowstone supervolcano. That is overdue as well. And the San Andreas Fault is also overdue. But these are with error bars of many tens of thousands, if not hundreds of thousands of years. So, yeah, we don't expect... Well, the probability that something will happen within our lifetime is fairly small.
I reiterate my answer that you shouldn't worry about it.
Yeah, I think I agree with that.
All right, questions?
Hi, so this is also about recent news articles about this black hole swallowing a star. Have you guys seen that and thoughts? It's like the first images of a black hole eating a star.
Is it about a TDE? So I'm not entirely sure which news article you're talking about, but there are phenomena in the universe where you can have black holes, either ones that are from the death of a massive star, which is a stellar mass black hole, or more supermassive black holes that can basically rip up a star that's orbiting in the vicinity, and this is called a tidal disruption event. And there are lots of surveys that are picking up these kinds of TDE events, which have a very characteristic shape in the light that comes out of these events over time. So what is essentially happening is once a star falls within what's called the tidal radius surrounding a black hole, the gravitational forces will essentially rip up the star, and it will half of the mass in that star will be swallowed up into the black hole. And when this happens, you see a flash of radiation as light is emitted, and that's called a tidal disruption event. There are problems with trying to, when we see explosions in the night sky, whether it's supernovae explosions or just bright flashes, it can be difficult to disentangle whether it is a tidal disruption event or just some burst of accretion phase. So for example, in very supermassive black holes, you have accretion disks surrounding the black hole. And if you just have a phase where there's just a lot of matter being accreted suddenly, then that can also produce a flare that also looks like a tidal disruption event. So with all these sorts of events, it's very difficult to determine the true nature of them and whether it is from scenario A or scenario B.
So this question relates to the galaxy evolution. And studying the evolution of a galaxy, does it shed some light on the bigger picture of the evolution of the observable universe, because maybe the pattern is kind of repeating itself at a smaller scale in the evolution of the galaxy? Any thoughts about that?
So the question is whether we can learn from the evolution of a galaxy something more about even evolution on even larger scales. And what we are basically doing, as our main speaker also was addressing, the way to see the evolution of galaxies to basically look further and further away, because that's looking back in time. But we cannot wait here for galaxies to evolve. If we take a telescope now and we want to wait until a galaxy has, one specific galaxy has changed its life phase, so to say, that would mean we are waiting a significant amount of the age of the universe. So what we're doing is we're looking at many different galaxies, and from that we are trying to construct a timeline, looking both back and in a wider field. We're trying to construct, what's a likely scenario if we see these types of galaxies and these types of galaxies. Can we, for example, see any, is there a theory which can explain how one galaxy becomes the other galaxy? And one such theory is, for example, our Milky Way is a spiral galaxy. So it's more or less a flat disk, which is actively forming stars. Whereas in our in the nearby universe, we're seeing a lot of galaxies which are ellipses or round spheres, which have hardly any star formation in them. And from computer simulations, we can show that one of the main reasons why you can change the shape of a galaxy is by colliding two of these galaxies together, and just the interaction between the gravitational interaction between the stars forms up these two disks into a more spheroid thing. The other thing, if we want to then look at larger scales, or at the universe, the evolution of the universe as a whole, what we can do is look at where do we find all these galaxies, because the light we see, so the light-giving matter is only a small fraction of all the matter in the universe, what we call dark matter, but all of that interacts gravitationally. And actually gravity is on really large scales is dominated by this dark matter because there's just much more of it. So what you will find, or at least that's the hypothesis, is that all the light-giving matter, all the galaxies are specifically concentrated in the regions where the dark matter is most dominant. And from that we can again derive the structure of the universe, which we believe again is a result of these tiny fluctuations which we initially see in the cosmic microwave background.
All right. Any more questions? Oh, okay. I guess you first, and then him.
Hi guys. So this question is for all three of you, if you want to just kind of talk about it real quick. So in the research that you do, what do you feel is the most interesting compared to actual data sets that you guys work with versus simulated data sets? And what is the, I guess, ratio of what you work with? Is it 10% simulated, 90% real, or for each of you in your respective fields, what is the distribution?
So I hardly work with simulated data. So I'm either measuring new instruments in the lab, or I'm measuring light coming from our universe at the telescope, and then processing that to make pretty pictures, and then try to learn something from the pretty picture. So yeah, if there is simulations, it's usually collaborators who do all that work, or literature. I mean, in some cases you want to compare to that, but mainly for me it's observation and measurements in the lab.
Yeah, I think you caught a panel of observers mostly here, but it's an interesting question because for most people it is sort of a blend in one way or another. So I work almost entirely with observational data. I look at radial velocity measurements of stars, which basically are a lot of measurements over time of whether a star is like moving towards you or away from you, and use that to look for evidence of a planet. And that's all real data. But one thing that I do that's kind of simulation is when you're looking at that sort of those measurements of a star's radial velocity over time, you don't just want to know whether there are planets there, like that you can see. You want to know what planets might be there that are leave too faint a signal to pick up in your data, because all data is noisy, right? All data is kind of junky and has errors and some scatter. And like I could see, for using this method, I could see Jupiter orbiting, a Jupiter equivalent orbiting a nearby star, but I couldn't see Earth because Earth is too small. It's not massive enough to make the star do something that's noticeable. And so the closest thing to simulations that I've been doing is sort of quantifying the edge of completeness of our star, so the edge of like where are the things that I definitely would pick up versus not pick up. And you do this by injecting fake planet-induced signals into your data. So you sort of add what a planet would do to your data set, and then you search for that fake planet and you see if you pick it up or not. And you can use that to sort of figure out like, well, I would find this planet, but I wouldn't find this planet that's 10 AU and the Earth mass away, and it's kind of a simulation.
Yeah, so I'm also an observational X-ray astronomer. So I primarily use data from this X-ray satellite called NuSTAR. And what I do is X-ray spectroscopy. So look at the light that X-ray photons give off as a function of their energy. So what I think that's really cool about the data that I work with is that the NuSTAR telescope is very special class of X-ray telescope in that it's the only one that currently exists that can focus really high energy X-rays. And because of that, that means that I can look at an AGN, a supermassive black hole, and I can construct a spectrum with data from the very highest X-ray energies, which no other X-ray satellite can do. And this is really useful because it can tell us information about the material that's accreting onto these supermassive black holes, and that's information that we can only get from the high energy part of the spectrum. Again, like I said, I do mainly work with observational data, so like doing X-ray spectroscopy, but occasionally I do dabble in simulations, so we sometimes want to know, like, when we look at a particular type of AGN, what the simulated spectrum of it would look like, and so we can use software to produce fake spectra under different sort of initial conditions, for example. So yeah, that's mainly observation, but a tiny bit of simulation too.
Hi. I'm not really sure who to address this question to, but it's about gas giants. And I'm curious, how do they fix longitude on a gas giant? What do they use as a point of reference? Like, this is 0 degrees longitude on a gas giant whose surface features are always moving around and changing.
So if I understand correctly, the question is, in a really massive gas giant planet where the surface is not solid, how do you measure sort of angular position on the planet in a way that matters? So that's a good question, and I think it seems like at the heart of it is the idea that if something's a gas giant, if it's a planet that sort of its outer layers are dense hydrogen helium gas, then that means that it's all swirling around in every direction, right? So what's actually the case is that gas giants have clear axes of rotation, just like rocky planets. So there are a couple of different ideas about how planets form. For some planets, we think we have a pretty good idea that they form via sort of a collapsing cloud of gas. For some planets, we think they form via pebble accretion. For smaller planets, like a bunch of rocks slamming into each other, making bigger rocks until it's self-gravitating. And for some, we're not sure. But in all these cases, I'm actually not entirely sure about this, but I'm pretty sure that it's predicted that almost all planets will have some clear axis of rotation, and therefore even a gas giant, which has a gaseous swirling outer layer, has a clear axis of rotation. So like Jupiter, for example, is a gas giant, but if you look at pictures of Jupiter, you see these really clear bands on it, right? It's like if you, I don't know if it was visible tonight, but if you're ever at our events and you see Jupiter, even through our telescopes and when it's barely resolved, you can see horizontal bands on it, which means that those are basically striated layers of different compositions of gas that are moving at different rates, but they're all going like this. So, for example, even the sun, which is literally just even more than a gas giant, it's just a big ball of gas, has an axis of rotation. The sun has an axis of rotation that's almost the same as the Earth. The Earth is slightly inclined, but we still have a clear axis of rotation. So to answer your question, just because something's gaseous doesn't mean that everything is sort of moving all over the place. Sort of rules of classical physics tell us that if something has even a little bit of angular momentum, meaning sort of rotational inertia, when it forms, it's going to keep that and preserve it very strongly, unless something radical changes that, like a collision or something like that.
Well, I get that what you're explaining, that would kind of easily explain latitude, how they measure latitude, but the actual longitude, like for the Earth, it's London, for where we measure longitude from. Wouldn't they actually have to see some kind of surface feature and, okay, that's it. We measure longitude from this spot. Do you understand what I'm saying?
Yes, thank you for the clarification. I switched longitude and latitude in my head, so sorry about that. So latitude is the up and down. Longitude is the around. I can never get this right. But so I guess an answer to that question.
Latitude is this way, longitude is this way.
So no, in that case, then
the equator, that's latitude, right?
Yes.
And
okay.
The Greenwich meridian, that's longitude.
Yeah. Okay. So
longitude runs from pole to pole.
Right. So in the case, so my question then answers longitude, but to answer latitude for Jupiter, for the gas giant in our solar system that we can look at, well, I actually don't know how solar system scientists do this. It might have to do. There are clear features on Jupiter. There's the storm, I guess it would change over time.
I think the problem with gas giants is because they're so dynamic, the surface features are constantly changing. So I don't think you really have a single point of longitude like a meridian, because even if you took the great spot doesn't stay in that spot always. So, like, long answer short, I don't think you can define like permanent lines of longitude for dynamically changing systems in a gas giant.
Can I ask a follow-up? One more follow-up.
Sure.
If you can't really define longitude very well, how do they measure the rotation of the planet? How do they measure how long its day is?
So I think the surface of Jupiter changes over a long enough time scale that you can see the bulk rotation even as the surface is changing. And so I would imagine, I'm sort of spitballing here, but there have been multiple NASA missions that have done flybys of Jupiter and have taken detailed imaging maps of the surface. And so you can sort of use those as reference points to look at the rotation of the planet over time, and that surface might change over time. But if it changes, if the surface changes slowly enough over time, then you can still watch the entire surface sort of rotate as a whole. A planetary scientist could answer this question better than me, but
can you do radial velocity measurements on different points of Jupiter's surface? Or is that too slow?
No, you could. There's something called an RM. So for I'm thinking now for exoplanets rather than planets in our own solar system. But there's a kind of measurement called an RM measurement, which I actually forget what it stands for, but it sort of does just this with extrasolar planets. So as a planet, not for its rotation, but as basically you can measure. No, actually, this is something different. No, and I mean on Jupiter, you wouldn't need to look at the spectral radial velocity, because if you can get the rotation rate, you know how big Jupiter is. So on its edge, you know how fast it's moving towards you or away from you.
Yeah. So one thing I have to add. Okay, so you look at Jupiter. It has a disk, like so. Okay, it has a disk like this. So suppose right now you see a red spot right here, right in the middle of the disk. Then you wait and you wait and you wait, and the red spot moves away behind the planet, but eventually it's going to come back to the same spot. And you see how long it takes to come back to the same spot, and that's how you measure the rotation period. Yeah, you don't need to define longitude. You can just wait to see how long the spot takes to come back to the same spot. Now, if you do that, it turns out that there's something called differential rotation. So at different latitudes, the rotation period is different. And for the sun, for example, the rotation period at the pole is around 10 days longer than it is at the equator. So in that case, there is no good way to define longitude. If you want a way, you have to make it latitude dependent, which then it doesn't, it's not a longitude anymore. So one type of planet for which you could define a longitude is a type I study, which is how Jupiter's orbiting their stars on very short orbits. And if they're orbiting on very short orbits, they are tidally locked. So the same face of the planet always faces the star. So for example, when the planet goes behind the star, we know that at that moment, the substellar point on the planet is directly facing us, because think about the geometry. So even in that case, there is no way to observe the planetary interior, but we know from physics that because it's tidally locked, the rotation rate of the planetary interior must be the same as the orbital period of the planet. Right, okay, next question. Anybody from the back? No? Anybody from the front?
You mentioned the capabilities of the satellite use being unique in terms of energy output. And so I'm just curious, how does that work? I don't know, from an engineering perspective, is the reason it's so much better than other, maybe elder satellites? Is that like control of a nuclear fuel source, or the ability to focus those rays? What's the?
Yeah, so basically it's the latter. It's about this telescope basically has the ability to focus very high energy X-rays. So you think of X-rays, you imagine them to be very penetrating. They just go straight through things, right? And so it's because of that, it's really hard to bend X-rays, and it becomes harder the higher the energy of the X-rays. If you go beyond X-rays and think gamma rays, you can't even focus them. So the gamma ray telescopes that we have in space, they're just essentially collimators. So they're tubes that just collect light. And a previous, other X-ray instruments that do collect high energy X-rays are also like gamma ray detectors. They're just literally just tubes that collect light and use things called coated aperture masks to just look at the shadow images that are left as these X-rays fall on the detector. So what's special about this X-ray satellite NuSTAR is that the optics have been engineered to be able to bend these really high energy X-rays. So the way the optics are constructed is there are many concentric shells of two different types of materials, a high density material and a low density material. And what this essentially does is enhance the overall reflectivity of the mirrors and enable you to basically bend at a sort of grazing instance these really high energy X-rays. And so, yeah, right now the NuSTAR telescope is the only telescope able to bend these really high energy X-rays. So other telescopes, X-ray telescopes that are also in operation that do focus X-rays can only focus the lower energy X-rays. So this critical angle that you can bend X-rays, it becomes smaller and smaller as you increase the energy, and that's why it's really hard to bend them.
All right, so if you're wondering what that rumbling sound was outside, it's actually the official start of the Caltech school year, so we're having fireworks. All right, any more questions?
You can ask general questions too about our lives as astronomers or anything like that. It doesn't have to be specifically physics.
What did you think of Ad Astra?
I want this one. Okay, this is a great question. He asked, what did you think of Ad Astra, which is a new movie starring Brad Pitt, in which, we're all friends here, we don't have to care about serious spoilers, but in which he has to go to Neptune to retrieve his father, who might be crazy and might destroy the world. So many thoughts. I thought that some things about this movie were actually really cool. So visually, it's an amazing space movie. They do some stuff on the moon, and apparently, the director took care to sort of shoot when they're driving on rovers. He shot in high frame resolution, and then slowed things down to about the sixth the speed to make it look like it was actually low gravity. Because in low gravity, things take longer. Things takes longer to fall to the ground. I thought that was all cool. Brad Pitt is always great. But as an astronomer, there were a couple of things that bothered me, and that's fine. That doesn't mean it's not a great movie. The one thing that bothered me probably the most is that at the end of the movie, they show photos of exoplanets that he took, and that apparently he was only able to take because he was on Neptune. So the thing about that is you need I never actually did this calculation, but getting to the edge of the solar system doesn't mean you can suddenly sort of... exoplanets are very far away, let's put it that way. Let's pretend you'd need a telescope on the order of the size of some fraction of the solar system to have enough of a focal length, to have the right focal ratio to actually resolve an exoplanet, and even then I don't think you could do it. So that got my goat just a little bit. But it's a great movie. I don't want to rain on anyone's parade. It's fun. You should go see it. No, it doesn't matter. It's just a movie.
Anyone else?
I guess each of you can take turns answering this. What got you into astronomy?
Well, I think for me it was a combination of the lectures my university offered and my general interest in astrophysics. So I started a bachelor in applied physics, and they offered the possibility to do a minor in astronomy. So I thought, well, that sounds cool, so let's try the first year course. And then I thought, this is actually kind of cool. So I took the second year course, and then I think the thing I liked the most is that for me, physics was very much different courses. So you treated electromagnetism, you treated fluid mechanics, you treated classical mechanics. And astrophysics was cool because then you grabbed bits and pieces from all these courses and you stuck them together, and then suddenly you had stars that worked, and you had galaxies that worked. And I think that sucked me in. And then the second was that astronomy is an extreme driver for technology. And that's my second motivation. That's why I do instrumentation. Like, that's sort of the perfect combination for me.
Yeah, for me, I think it was just a couple of really good professors. Like, I was into physics in high school just because, I don't know, I liked reading about physics stuff, and I didn't think much about astronomy. I mean, I liked like cosmos and stuff like that. And then I got to undergrad, and someone recommended I take this freshman seminar that met for like 3 hours every other Monday night. And it was like in this old small observatory, and this professor who was in his 60s and super charismatic would like give short lectures at the beginning and then just have us go to the board and do what we call back of the envelope problems, which is a big thing, I don't know, in physics, but particularly in astronomy. The idea is that all these problems are really complex, right? Like, stars are incredibly complicated things. We don't fully understand how planets form or how galaxies evolve. But if you basically pull from all the different areas of physics that you were just talking about, and you say, okay, I know a few basic rules about how the world works, and make a bunch of assumptions, then you can sort of, using very simple physics, work out answers that turn out to be within a factor of 10, right? It's what we call like order of magnitude, like within a factor of 10. Like, you can get like more or less what we consider more or less the right answer. And this really excited me for a couple of reasons, one of which is, I was only a freshman. I didn't know that much complicated physics or calculus or anything, but like, you learn a couple of simple kinds of physics, you understand them, and then you sort of take these rules and do basic math, and suddenly you can figure out, okay, what's the lifetime of our sun? You can actually figure that out within a reasonable degree using just freshman year physics. And I really like the idea of a field where like there are really complicated ways to answer these questions, but you also sometimes just say screw it and throw out the details and pretend that things are simple and wind up getting an answer that is informative and exciting. And I really like the idea of sort of like rolling up your sleeves and solving a problem, even though you're not doing it 100% correctly. You sort of treat it with the idea that perfect is the enemy of the good, and that sort of makes it easier to move through ideas and solve problems. And then I took a bunch of classes, and I really liked it, and I was like, this seems fun. I'll do this more.
Yeah, so for me, I got into astronomy pretty young. So since I was a kid, I was always fascinated by the night sky and by the vastness of space. And so, when I was maybe a preteen, went to the local library, and I picked up this book on the universe that was filled with these really high resolution HST images, and it was just mind-boggling for me. And I think one of the standout images from the Hubble Space Telescope that really kind of sticked with me and sort of kind of pushed me into continuing studying astronomy in later years was the famous Hubble Ultra Deep Field image. So what this was the Hubble Space Telescope basically took a seemingly blank patch of the sky and stared at it for 11 days. And the end result was this beautiful image with thousands of galaxies looking down across a 13 billion light year corridor. So we're seeing light from not too long after the Big Bang. And it also really fascinated me how the further out we look in space, the further back in time we are, and how we can build up a picture of the evolution of the universe by looking further and further out into space. And so I always had that sort of curiosity throughout childhood, and then I studied physics in undergrad with the intention of going into grad school and studying astronomy, but I didn't want to be too narrow and just purely major in astrophysics. So I started off by getting like a general knowledge of everything in physics, and then specializing in grad school.
More questions?
So this question is for you, Nikita. What specifically about black holes do you study?
Okay, so the kind of black holes that I study, active galactic nuclei, are very supermassive black holes. So approximately 10% of all galaxies are what we call active galaxies, or AGN. And so we believe that at the centers of most galaxies harbors a supermassive black hole. AGN are galaxies that these supermassive black holes are actively accreting, so they're accretion disks where material is falling into the black hole and feeding it, and as material falls into the black hole, basically radiation is given off. So I study these active galactic nuclei in the X-rays, and the reason why we study them in the X-rays is supermassive black holes in AGN, they emit light across all the wavelengths of the electromagnetic spectra, but X-rays are particularly useful wavelength to study AGN because by looking at the spectrum of X-rays, you can elucidate a lot of information about the nature of the material surrounding the black hole, what's its geometry, and how what kind of light we're seeing from them. So, you know, there's this very commonly adopted model for these supermassive black holes called the unified model of AGN, where we see like different types of AGN with different properties. There are two main types, type 1 AGN and type 2 AGN. And type 1 AGN, the way we differentiate between type 1 and type 2 is that we can see certain emission lines in the optical spectra in type 1 AGN, and these lines are very broad because material is moving very fast close to the black hole. But then in type 2 AGN, we don't see these kinds of broad lines. And so in this unified model, the idea is that the reason why we see broad lines in one type and we don't in another is because there's basically a donut of gas and dust surrounding these supermassive black holes. And so with the type 1 AGN, we're looking at this donut face-on, and so we basically have an unobscured line of sight. And then with the type 2 AGN, where we don't see the broad lines, we're looking edge-on through this donut of material. And so basically we're looking at an obscured AGN, and we can't see the broad lines anymore. So yeah, we can look at these sources in the X-rays and look at how they're absorbed and whether they're not absorbed, and learn more about how valid is this simplified unified model, what are like the kind of holes in the theory, can it explain our observations or not.
Questions?
Okay, so with dark matter, is there any evidence that dark matter can fall into black holes?
Dark matter can definitely fall into black holes, just as with regular matter. I think observationally, it's hard to find signatures of dark matter specifically from black holes. Obviously, there are many ways that we for example, there's this phenomenon called gravitational lensing, where it's basically a general relativistic effect where light gets bent by the very strong gravitational field of, say, a cluster of galaxies or even a single galaxy. And that light bending is basically governed by the distribution of dark matter, because there's much more dark matter than visible matter. And then another way is if you think that dark matter is a particle, then it would have a corresponding antiparticle, and this particle and antiparticle would annihilate each other by particle physics theory, and this would produce gamma rays. And so you could take a gamma ray telescope and look for these annihilation features that would appear. But in the case of a black hole, this would be hard to disentangle, because you do have dark matter annihilating and producing gamma rays, but you also have regular particles like electrons and positrons that can also annihilate and produce gamma rays. And especially with a black hole, you've got like very high energy radiation being emitted, and particles are also at very high energies, and so it's, I think, more observationally difficult to determine that.
Any more questions? Anything?
Yugon, you didn't talk about how you got into astronomy.
Is that what you were trying to answer? Okay, so yeah, maybe I can talk about that. So I entered astronomy early when I was a kid. Basically when because I was an amateur astronomer, and I loved doing astrophotographing, even though I'm now getting, even though not aging like that much, but I mean psychologically a little bit, so not doing that very frequently anymore. Not like our speaker today. He's still, even though he's a postdoc, but he's still very energetic on that. So I got into this thing when I was a kid, when I went to a planetarium in Beijing, and that's basically the start point when I saw, because I was probably only this tall, and I saw those big pictures, like I think the Voyager took the pictures of the planets, and basically it was very shocking to me to just see those big giant balls of very amazing planets up there. So that's when I got into astronomy, and I went to study astronomy major when I was in Peking University, and then came here as a PhD student. Maybe, did you introduce, so for example, maybe I can ask a question. What's the most recent scientific astronomical questions you were trying to figure out?
Okay, I can. I haven't, for the last year, I've not so much been trying to answer one specific question as put together a sample of planets that I can use to answer a couple questions. So for the project I've been working on is basically counting planets around stars and actually searching for new ones. So I've been looking at this sample of about 800-ish of the nearest, brightest sun-like stars, so things that are about the same mass as the sun. And these are things that have been observed by radial velocity instruments, sort of taking those sort of back and forth in time measurements over the past 20 plus years. And people have been studying them for a while and have found hundreds of planets around them, but it's been a while since someone looked at the the sample together as a whole. Like it was 2008 when someone did this, and they did it to sort of try to figure out. There was a long enough baseline at that time that they could find in that data set planets that have orbital periods out like between Jupiter and Saturn, basically. And you can use that to sort of figure out, are there more planets further out, or are there further out than further in, or are there fewer planets? And they've sort of found that the number of planets, particularly gas giants that you were talking about, Jupiter, things that are like Jupiter or bigger, actually rose as you get further away from the host star, and peaked right around the place where where water freezes. So peaked right at the edge of sort of the habitable or temperate zone where you can have liquid water. And so that was interesting because you'd say, oh, there are a lot of planets around what we call the snow line, which is where you get snow or ice. But they didn't have a long enough baseline to look for planets further than that. And so they didn't know, does it keep rising after that or does it fall off? And that can tell you about different theories of planet formation. And so I've been working with some of the people in my research group to revisit the sample 10 years later. And 10 years later, we have a long enough baseline that you can actually find planets out there. And so we've bbeen trying to see, do you have, so we know you have more gas giants right around the snow line. Now, do you have more out beyond it, or do you have fewer? And so preliminarily, we found that you have fewer, which is interesting because it means that like you get a lot of planets right at the edge of where I'm not entirely sure what it means, but it can inform ideas about how planets form. And so to answer that question, all I've been doing is sort of searching for planets around these stars. I've actually found a couple new planets, and I'm working on a paper for that, so that's been fun. And then just counting them in fancy math ways.
Yeah, so I guess my thesis sort of focuses on two different types of avenues to explore AGN. So one is, I talked about how there are like two different classes of AGN, the type 1s that are supposedly unobscured because we're looking at them face on, and they're unobscured in the optical, and then there are the type 2s which are obscured because we're looking edge on through this torus. But there are a number of AGN that fall into this category where they seem to be type 1 from looking at their optical spectra. They show broad lines, but if you look at them in the X-rays, they have a spectrum that looks like a type 2 AGN. So I'm looking at these sort of mismatched classification AGN to see why is it that the classification that we get from looking at their optical spectra doesn't match those in the X-rays. So I try to use broadband X-ray spectroscopy, but also look at other features at other wavelengths, such as the infrared, to see what could explain this possible mismatch between X-ray and optical classifications. And then the second sort of area that I'm focused on with AGN is I look at sort of samples of AGN that are nearby, and I look at these. I look at the type 1 AGNs because we think that they're unobscured. It's basically their spectra are a little less complicated in the X-rays than the type 2s. And the question I want to answer looking at this sample of AGN is basically look at properties like the X-rays that we actually see from AGN are, we think, produced in this hot plasma of gas called a corona. So you might recall the sun has a corona, which is a very tenuous upper atmosphere that's very hot. So we think there's something similar like a solar corona very close to the black hole, and this is what's producing the X-rays. And I want to answer questions about what are the fundamental properties of this corona. So while it's the kind of powerhouse of this supermassive black hole producing all the X-ray radiation that we see, a lot about the properties of the coronae are not known at all. Like, we don't know what its temperature is, we don't know what its geometry is, we don't even know very well the physical mechanisms that's producing the X-rays. So I'm trying to look at this like large sample of nearby AGN, study them using X-ray spectroscopy to see whether we can answer questions like, you know, what can we constrain the temperature of these AGN coronae and other properties of them.
Yeah, so I'm also working on two things, but they're significantly more distinct from each other. I'm currently a lot of the time in the lab trying to build an instrument with which we're trying to get the third dimension to our invisible universe. And what I mean by that is that when we look out with our eyes or with the Hubble Space Telescope, we see a lot of galaxies. They're all emitting light in the visible, which you can see with our eyes. But about half the light coming from galaxies is actually in the millimeter or submillimeter regime, so a much longer wavelength, much more similar to the CMB radiation. And that's from galaxies which have a lot of star formation, but also a lot of dust. So most of the light of the young new stars is actually absorbed by the dust that heats the dust. That means the dust starts radiating. But it also means that the only way we can see these galaxies is by the radiation from the dust, which is in these millimeter waves. There's been telescopes, and there's a lot of telescopes now which can take a 2D image of this. The problem is we want a 3D image because we want to see the volume of the universe. So for that we need to build spectrometers, and I'm working on what we call an on-chip spectrometer. So instead of building a classical way to build a spectrometer is to take, for example, a grating, but a grating for submillimeter wavelengths would become the size of a meter approximately, so a meter cubed. And the trick is that everything around us is also radiating light in millimeter waves because we're all warm bodies. So we need to cool this meter cubed grating down to at least 4 degrees above absolute zero, which is quite an undertaking. So what we're working on here at Caltech is trying to use clever electronics to basically reduce that grating into a computer chip. So that's one project I'm working on. The other is a bit like Nikita. I'm looking at a sample of active galaxies, but I'm not looking for them in the X-ray, I'm looking for them in the radio waves. And there's a distinct difference. So Nikita was talking about type 1 and type 2 AGN, but all of these AGN emit enormous amounts of X-rays, enormous amounts of optical light. But if you look in the radio, you can actually find a type of AGN, which we call the radio mode AGN, which only emits radio waves. And we predominantly find these things in the most old, red, massive galaxies. However, if you look long enough, you find a few of them in actively star-forming galaxies where typically the AGN which Nikita studies are found. So what I'm trying to figure out is why do these AGN, which are typically found in things which don't form stars, why are they present in a galaxy which is forming stars? And why didn't it turn into an actively radiating AGN? And getting a lot of optical data, or both optical, infrared, radio data to try and figure this out.
Are you well supported in your studies? When you talk about needing to do something and you're building something and you're looking, is it easy to get access to the equipment that you need to do that? Do you have to get grants? Is there?
It's yes and no. In principle, the way this works is that if you want observational data, you need to get time on a telescope, and that means in general that there's only so many hours of night or day in a day, and so every astronomer who wants to do something with a telescope needs to write a proposal. I want to do this for this reason, it will solve this mystery, and I need so much hours of the time on the telescope. And that then goes to committees of wise men, we would call in the old days. In the current days, it's more generally still somewhat senior staff, but more diverse. And they judge which proposals get the time because they think it's most promising. And then there's a difference in how large a fraction of the population, or how large a fraction of the people get the time. So everyone is well supported in trying to write these proposals, but the large telescopes like HST or ALMA are oversubscribed by factors of 7 to 10. So there's 10 times more time needed to execute all the projects than there actually is time.
Just sort of a follow-up on that. I think all of us here are pretty lucky, in this respect, are pretty lucky to be at Caltech or JPL, which is actually Caltech institution. One, because the professors or PIs here are generally pretty successful at grant applications and able, thanks in part to Caltech, but also to their own work and and postdocs and people in their group who help them work on, and grad students who work on grants are pretty good at bringing in money to pay for grad students and postdocs and also equipment. But on the other hand, Caltech also is sort of known as being a bit of a powerhouse in observational astronomy and building observatories. So on the radio side, there's Owens Valley, which is in Central California, is a huge radio observatory. It sort of provides everything that you need. And then Caltech, along with the UC system, is one of the primary partners in the Keck Observatory in Hawaii. And having that primary partnership, just like I couldn't do any of my research without access to Keck. And we're really lucky that we have access to observatories like this, and it basically makes the process easier than if you're applying. If you weren't at Caltech or a UC institute, then you'd have to apply for time on these ground-based observatories through NASA or NSF, which is the National Science Foundation, slices of time, and that's extremely competitive, as it is with space-based telescopes. And so we're pretty privileged to be grad students and postdocs here in that respect.
So I was watching some YouTube stuff on the odds of finding life elsewhere in the universe, and they went through kind of some quick rough math of the different variables that are needed and multiply those all together, and basically that was the same number of, it's 1 in however many, and that was how many planets there are. So basically the odds were the only planet that could support life in the universe. But then I saw something else that said, life could also form not on oxygen, or not in oxygen environments, but in methane atmospheres as well. So, how many methane atmosphere planets are there out there versus oxygen, or do we know?
So that's a really good question. So the question in a broader sense was, how do we search for evidence of life on other planets or calculate the odds of it? But then the specific cases, methane on other planets. The answer, I don't study exoplanet atmospheres, but as I understand it, at the moment there are only certain. It's really, basically, the short answer is it's really, really hard to characterize the atmospheres of exoplanets, because the only way you can do it is the exoplanet has to pass in front of the host, between us and the host star, so that you see the imprint of its atmospheric spectrum as absorption lines on the star's spectrum, which is many orders of magnitude brighter, dominates by many orders of magnitude, and so this is a really noisy problem and under-constrained. I could be wrong on this. I would go and check, look this up after the fact. But I don't think there are good constraints on methane-dominated atmospheres at the moment. There was recently a really exciting announcement that there was a water detection, liquid water detection, in a planet that was orbiting an M dwarf, which is a star that's much smaller and noisier than our own, and the planet was in a place that in a temperate separation, so you could get liquid water, and that's exciting. So we're getting there very slowly. There's a telescope called JWST that might be launching shortly to the, you know, we'll see when it actually launches, but it's specific. One of its primary missions is to, it has an infrared spectrograph that can be used to get very precise spectrum of exoplanets as they transit in front of their host stars. So I think that there's work ahead where you could start to try to measure the abundance of elements like nitrogen and oxygen and methane. You didn't really ask this, but just for a general answer to the first part of your question about like the thing that you were describing, I think, is the Drake equation, where someone sort of came up with this is sort of a back of the envelope thing, where like estimating the number of planets where you could support Earth-like life. None of us here are an astrobiologist, but I think any scientist who gives you a number when they ask you you ask them the odds of finding life somewhere else is just not being a responsible scientist. Like, we just have no idea whether there's life anywhere else or what it would be like. Like, what are the odds that it would be like us? Like, I don't know, personally it seems unlikely, but I have literally no idea. And there was just, if you're interested in learning more about the search for extraterrestrial life or habitability, there was just a couple of days ago a really great New Yorker article broadly about SETI, which is the search for extraterrestrial intelligence, and specifically about this professor, Jason Wright, who's sort of pioneering an effort now to try to sort of formalize the field and make it sort of basically publish a canon of papers that you could use to sort of treat SETI like you would any other field of science and sort of finally get it the funding that he thinks it deserves. Because it's there's not much funding in it, and it's partially due to like PR pushes in the 80s and the 90s. And we live in an interesting time for this because the field of exoplanets is exploding and we're getting pretty good at these atmosphere characterizations, and at the same time there's a push to try to, like, my advisor actually did his PhD on SETI work, but he decided to go into more classic exoplanet stuff because it's hard to be a SETI researcher because you either become the most famous person in the world, or far more likely you're never going to actually find anything in your research. And that doesn't mean it's valueless, but it's a different kind of scientific problem.
Let me add something. The first time I learned the Drake equation, which is the multiplication of all these factors, is probably well over a decade ago, when we were just starting to find the first exoplanets. And then the multiplication went like small number, small number, small number, small number, small number, almost nothing. And since that course, as he said, the field of exoplanets is exploding, and we're starting to find extremely more. The number of exoplanets is higher and higher. 4,000. Yeah, and I think it was 10 then. And the conditions under which we see planets orbiting stars are much broader than we initially expected. So all these numbers are going up all the time at this moment. So, as he said, it's completely unpredictable where that would end, but my take on this question is always, it's a very small number, probably, but the universe is very big.
All right, cool. I think it's time to wrap it up. Let's thank our panelists, and also thank you all for coming.